Trusses. In the previous classes, what we learn is finite element method basics, and we consider the one-dimensional elements, the bar elements, the derivation of shape functions, and derive these stiffness matrix, and derive the governing equation of motion to solve the any one-dimensional problems like bar. So, and we learn the solution to the particular problem with the different boundary conditions. So in this class we'll start with learn into this trusses and beams. In this, first we'll start with the trusses. What is a truss? Simply we can say that truss is a structural member which is used to carry the loads. That loads may be a compressive loads or tangential loads. So this is the truss structure. It is a truss structure. So this truss member, it is one, we consider this is one is the truss member. This truss member subjected to a tensile force or a compressive force. So once we may see that these are many applications in our daily life, like railway bridges, roofs of the buildings, and some shades. We may see the many in our daily life. So to derive the stiffness matrix for this truss members is a very important thing. So in this session we will learn the how to derive the stiffness matrix for this truss member. So this is the truss members. Now for this analysis, here we consider truss that member is and two-dimensional members because it is very common type of structure. So we may see that already we discussed in the, we can find out these applications in railway bridges, transmission towers also we may find out. So this is an two-dimensional analysis we consider in this case. So the definition of this truss is already we defined. This is a structure that consists of straight members connected together with pin joints, and it sends and it carries the loads. And one more important point here is this truss members, the area is negligible when it is compared with loads, because these truss members carries the heavy loads. That is also one of the important parameter in this one. So the forces may be external forces, internal forces. The external forces means subjected to compressive or tensile loads. Sometimes it may be considered the reaction supports. We will all consider all these things, and it's also it develops some internal forces with different components together. So in addition that, first we try to understand, derive the element stiffness matrix for this truss member, one member. So once we know this truss member element stiffness matter, and later we can go the assemble this all the element stiffness and apply boundary conditions and loads, and we can find out the solutions, what are the deflections at the different nodes. So this truss member, first what we understood is, first we have to derive the relation between the local and global coordinates of these truss members. For understanding purpose, we consider here this is 1 this is a truss member, node 1, node 2. So at node 1 we may say that it is a displacement in global coordinates, u1 displacement, and y direction v1 displacement. So v1 u1 are the displacements at node 1. So but actually the resultant displacement is in this direction, along this member direction, that is q1. So now we have to find out this relation between this global coordinates and local coordinates. Here the local coordinates we may say that q1 is the along its axis of this truss member, u1 u2 are the global coordinates like x and y axis. So first we have to understand, derive the relation between these two coordinates. First suppose u1 is the, what is u1 is u1 displacement along x-axis, and this one is v1 displacement in y-axis. So the total resultant, is q. This is from here to here. So we know that here is theta, because it makes some angle with its horizontal surface. It is theta. Theta is the inclination angle of this truss members. So we need to find out this one. So suppose to here. So this, suppose we may A B C, A B C. So AB is the distance plus BC. Total will gives the Q1. So here we can say that Q1 is equal to AB plus BC. So AB is equal to U1 cos theta, BC is equal to V1 sin theta. So from this triangle we may say that the local and global coordinates relations, Q1 is equal to U1 cos theta, V1 sin theta. So this is the equation 1 from this coordinates. Q1 local coordinates, displacement along its axis of the truss member, is equal to its sum of U1 cos theta plus V1 sin theta. So similarly at node 2, because we consider here is a 2 noded truss members, so this is the equation 2. So this is the also Q2 is equal to U2 cos theta plus V2 sin theta. So from these equations we can rearrange the relation between this local and global coordinates. Q1 Q2 is equal to cos theta sin theta 0 0. This equation we may rewrite as Q1 V1 in terms of its matrix form. Simply we can rearrange into matrix form. So here is cos theta sin theta, cos theta and sin theta. Cos theta sin theta we can modify. For our simplicity, we can write it as cos theta is as a C, sin theta is termed as S. So this equation is simple. For the simplification purpose, we can rearrange this equation is Q1 Q2 is equal to CS 0 0 0 0 CS V1 U1 V1 U2 V2. This is the relation between the local and global coordinates. So once we know this relation, we can easily find out the element. So this is the relation Q is equal to L delta. What is Q? Q is equal Q1 Q2. This is the local coordinates. Delta is global coordinates U1 V1 U2 V2. So L is the transformation matrix in between the local and global coordinates. So L is equal to CS 0 0 0 0 CS in the matrix form. So this is the relation between the local and global coordinates. So from the strain energy, concept of strain energy in one dimensional bar elements, already we derived this element stiffness matrix from that equations we are using. Once again, this is equation 4 from the one dimensional bar element. In the previous classes already we learned this is the strain energy is equal to half into U transpose. This is the stiffness matrix into U. So with this we can here these coordinates that has been substituted. Here this local coordinates are Q transpose, because in further generalized way we can U transpose mean coordinates is displacements of this particular elements. Here the displacements of the particular elements. So the displacements has been Q1 Q2. Here also Q1 Q2. So we can substitute this Q relations in this equations here and here. Substitute in these equations. So once you substitute, we will get this equation of delta transpose in the matrix forms. Finally, we will get this equation 5. So after substituting, we can simplify and multiply these equations, and also we can substitute this L matrix here, CS 0 0 0 0 S. So this is the final equation. After substituting, we will get this equation 6. So this is the transformation matrix. This is the B matrix of one dimensional bar elements. So this total term, it is called as, what is that? Element stiffness matrix. So this is the element stiffness matrix of this truss member. So this truss member's element stiffness matrix, we have to multiply with the transformation matrix and its B matrix. This is the B matrix minus 1 1 B transpose. This is the transformation matrix. So we have to multiply these matrices. After multiplying these matrices, finally we will get the element stiffness matrix. Element stiffness matrix. This is the matrix number 8. AE by L square into C square CS. This matrix is called as element stiffness matrix. Element stiffness matrix. So this is the important matrix to solve this trusses by using finite element approach. Once we know this derivation, remaining things are very easy.